Hey guys, Miss Marusik here, and in this video we're going to talk about the experimental determination of reaction orders for a rate law expression. Up until this point, we have been using mechanisms to determine what our orders would be for a rate law expression. We could look at the slow step, and by using the coefficients, we could assume that those would be the orders in the overall reaction. But here's the problem. For an overall reaction, I can't use coefficients. We don't know what the exact mechanism would be for that overall reaction, and so we can't assume that on an overall reaction the coefficients are the same as the orders. And so if I am not sure what that mechanism is, if I'm not sure what that slow rate determining step is, I'm going to have to figure out those orders in some different way. And so that's where we're going to be using experimental data. Now, for experimental data, we technically have two options. We have both differential and integrated. We're going to be looking at this differential equations today. These are involved when we have rate and concentration. And hopefully you notice that these equations look exactly like what we've been working with. We have some rate, which equals some rate law constant A, and then we have our reactant raised to some order. We're just going to have to figure out those orders in a little bit of a different way today. Now, for our integrated ones, you notice that we have some totally different formulas there, which those of y'all that are in calculus, those formulas might look a little bit familiar. We're going to talk about in a later video how that all ties together with this. But for today, our expressions are going to look exactly like what we're used to, where we have some rate equals k, a to the x, b to the y. If a or b is a substance, then of course we would plug in the identity of that substance. X and y are our orders. Now, some things that is in this little chart that we haven't yet used. First off, overall order would be our two exponents added up. So it's just simply the sum of the orders themselves. So if a problem ever asks you, what is the overall order of the whole entire reaction, you would just add up the orders themselves. Also today, we're going to see that on occasion, if we don't have molarity involved, we might have pressure for gases. Now, I'm going to re-emphasize this later on, but these brackets we only use for molarity, and so if I have pressure involved, I will instead use parentheses. We see this again when we get to our equilibrium unit, that distinction between using brackets for solutions with molarity and parentheses when we're dealing with the pressure of gases. One other thing that we're going to do today that we haven't done yet is actually calculate a value for the rate law constant. So you're going to see us get a numerical value with units of that today. Now, down here, if you notice, it gives us a whole bunch of various steps on how to solve these differential rate law expressions. However, what we're going to do is we're just going to jump into an example, and you're going to see that we're going to talk about all of these steps in the context of that example. So with that said, let's go ahead and look at our example. All right, so it says here that we have a reaction of A plus B yields C, and it wants us to find some various things about my rate law expression. Now, what I'm going to actually do first is go ahead and write myself kind of what the rate law expression would look like. I know that I would have rate equals some K. My first reactant is A. It's going to be raised to some exponent. And then I'm going to have B also raised to some exponent. Now, what you've noticed they have done here is they have run this experiment 4 different times with various concentrations of A and B, and that resulted in particular rates of forming product C. And you notice that they did take initial rates of these, because remember, rate always changes more at the beginning of the reaction than at the end. And so what we're going to do is by using this data to plug in for rate, A and B here, we're going to be able to solve K, our constant. We're going to be able to solve X, which is the order of A, and we're going to be able to solve Y, which is the order of B. And we're going to do so in a very set order here. So the first thing that it asks us to do is solve the order with respect to A, which means they are here asking us to solve X from this equation up here. And so to do that, what that means is that I'm going to need to pick some trials to plug in here, but that's going to leave me with 1, 2, 3 unknown variables for right now. And so what I want to do is I want to be strategic on picking 2 of these trials where I can start to get some of these variables to eliminate out. Okay, now K being a constant will always eliminate out. So that's good news there. But I also want to get this Y to eliminate out. And the way I'm going to do that is if I pick 2 trials where B stays the same, it will cancel out along with that exponent. So when they ask you to solve the order with respect to A, to one reactant, we want to pick 2 trials where B stays the same. Now, sometimes you have multiple options for that. You know, you can pick different ones. Here, I could pick 1 and 2. I could pick 1 and 3. Or I could pick 2 and 3. You see, I've got some multiple options there. I'm going to go ahead and just use 1 and 2. And I see that those 2 have B staying the same. And what I'm going to do is I'm going to set a ratio of 1 trial over another. Now, when I do this, I'm typically pretty strategic. I usually put the trial with the bigger numbers on top. If you notice, trial 2 has a bigger number than trial 1. And so what I'm going to do is I'm going to set a ratio of trial 2 over trial 1. And what I'm going to do is I'm going to plug in everything from these 2 trials into this rate law expression, but I'm going to set the 2 trials over each other. So first, let's plug everything into trial 2. Okay, so I'm going to start off with the rate, which was 1.865 times 10 in the negative third. That's going to equal some K. My A value for that trial was 0.10. That's going to be raised to some X that we're going to try and solve. My B is going to be 0.05 raised to some Y. And I'm going to set that over doing the same thing now for trial 1. So trial 1 had a rate of 4.66 times 10 in the negative fourth, some K constant. A's concentration was 0.05 raised to an exponent of X. B was again 0.05 raised to an exponent of Y. Now, here's the deal. K's will cancel. Those were constants, and it's going to be the same for all of these trials because we assume that all of these trials took place at the same temperature. As long as temperature remains consistent, then these K's should remain constant, okay? The other thing that will cancel is 0.05 to the Y and 0.05 to the Y. Regardless of what Y is, we know it's going to be the same. The order is the same for this reaction overall, regardless of what concentrations I'm using. And so therefore, this will also cancel out, which was the whole goal of picking 2 trials where B stayed the same. So look what this leaves us with. What I would do is I would take this math and plug it into my calculator. And when you do so, it comes out really, really close to 4. So then I would do the same thing here. 0.1 divided by 0.05 is equal to 2, and that is going to be raised to an exponent of X. Now at this point, when you're doing these problems, they're not going to give you any kind of weird orders here. Your orders are either going to be 0, 1, 2, 3, or 4. And very rarely is it 4. Usually it's 0, 1, 2, 3. And so if I can start figuring out what this exponent is, I would know my order to it. So what I want to do is I'm going to start plugging in things for x until I get 2 raised to that exponent equaling 4. Now, obviously here the numbers are pretty clean. Sometimes you do end up with decimals, and if you do, just start plugging in things until you get one to work, you know? Plugging your number raised to the 0, plugging your number raised to the first, plugging your number raised to the second, until you get one that works. Here, obviously, x would be equal to 2. And so what that means is that we can write a statement that says that this is second order with respect to A. All right, let's do another one. The next one asks us to solve the order with respect to B. Now, you technically don't have to have A cancel out here, but it sure is convenient if it does. I mean, obviously now we know that this A up here has an order of 2, and so I could just include that math as part of my work. However, let's go ahead and see if there are 2 trials where A stays the same, and so I can get them to cancel out. So I look here and I'm like, well, the only 2 I see would be 1 and 4. And again, I'm going to put the bigger trial on top. If I look at my numbers here, I see trial 4 has bigger numbers. You can see if you compare the 0.05 to the 0.10, that's pretty clear. So I'm going to put trial 4 over trial 1. By the way, the reason why I put that bigger trial on top is so when I get to this point over here, the numbers come out pretty clean. If you end up putting the larger one on bottom, what happens is that you end up with decimal numbers over here, and so sometimes that calculation isn't quite as obvious. All right, so now I'm going to do the same thing I did before. Trial 4 had a rate of 3.73 times 10 to the negative third. I'm going to have my K. My A for that was 0.05 raised to some X, which actually we know now is 2, so you could go ahead and plug that in. And then I had 0.10 raised to the Y. I'm going to put that over trial 1. Trial 1 again was 4.66 times 10 to the negative fourth equals K, 0.05 raised to the X. Again, now we know that X is 2, so you could plug that in. And then I have 0.05 raised to the Y. All right, so again, thinking about what's canceling out here, K remains constant, so that would cancel. 0.05 to the X, which again is 2, would also cancel. And so therefore, I'm just left with this math right here. Okay, so when I plug these into my calculator, this 3.73 times 10 to the negative third divided by 4.66 times 10 to the negative fourth gets a value of 8. 0.1 divided by 0.05 is equal to 2. And then, of course, that's going to be raised to an exponent of y. And so, again, I know 2 to the 0 would be 1, 2 to the first is 2, 2 to the second is 4, 2 to the third would be 8, and so therefore here I know that y is equal to 3. And so therefore this is third order with respect to B. By the way, you notice I am showing quite a bit of work as I set these up. I'm showing everything that's canceling out so you can kind of get an idea of where all these numbers are coming from. However, if you were actually setting this up as a free response question, you would not need to show these things that are canceling out. So what I have remaining here after I've covered that up is the bare minimum amount of work that you would need to show in order to earn credit. I would show which trials you are putting over each other. You want to show those rates over each other, and then you want to show your concentrations raised to their exponent. And then you want to clarify all of this information over here. So if you don't show those things canceling out, it's okay. However, I like to, because that way I'm going ahead and addressing how it ties back to that original formula, and I can double check that I made sure that I picked 2 trials where those values actually did end up canceling out. So the next thing it asks us to do is to write a temperature independent rate law expression. And so this is just with our X and Y plugged in. So I would have rate equals some K. My A had an order of 2, and my B had an order of 3. And again, if you had something other than A and B, like you actually had actual compounds there, then we would plug that in instead of A and B. All right, now the reason why this is the temperature independent rate law expression is because K is dependent on temperature. It's only got a particular value at a certain temperature. If I do anything to that temperature to speed up or slow down my rate, then obviously the K would also be affected. All right, so here's what they want us to do. They want us to solve for that rate law constant K with units. Now, to do that, what I'm going to first do is I'm going to go ahead and kind of rearrange this equation in order to specifically solve for just K by itself. And when I do that, what I would end up with here is that rate over A to the order of 2 and B to the order of 3 equals K. And so now what I'm going to do is I'm going to pick a trial and plug in to that information. So to do that, it does not matter which trial you pick. You could pick any of these that you wanted to. I would indicate which trial you picked, though, just so that way the grader could follow your work. However, I will tell you that because this is experimental data, if you pick one trial over another, you might see a slight fluctuation in the K, but for the most part, all of these trials should give you almost exactly the same number for that K. So what I'm going to do is I'm going to go ahead and plug in for trial 1. So plugging in for trial 1 had a rate of 4.66 times 10 in the negative 4th. And I'm actually going to go ahead here and include some units because I want to show you what happens with these units. That had a unit of molarity per second. Okay. And I'm going to put that over A, which A was 0.05 molarity, and that is raised to an order of 2. And B is also 0.05 molarity, and that's going to be raised to an order of 3. And so what I would do is plug all that into my calculator. 4.66 times 10 to the negative 4th divided by 0.05 squared, and also divided by 0.05 to the 3rd. Be really careful on your order of operations there. If you're going to plug this in all in a row, make sure to divide by the first thing and then divide by the second. Or the other thing you can do is put the entire denominator in parentheses. Just be careful on your order of operations, okay? What this does is it gets a value of right around 1,491. Now, let's talk units for a minute. I ended up here with molarity per second on top, molarity squared, and molarity third on the bottom. Well, think about this for a minute. First off, divided by seconds, that part's going to stay. But then I'm also going to have molarity divided by these adding up, molarity to the 5th. So molarity divided by molarity to the 5th would give me molarity to the 4th on bottom. One of those molarities on top and bottom would end up canceling out. Another way of writing this is 1491 seconds to the negative 1st, molarity to the negative 4th. By the way, you notice over here that we do have kind of a format you could use for the units for K. The unit of time is going back up here to, again, this initial rate, if it was in seconds or minutes or hours, whatever they used. And then you notice they mention molarity raised to the negative overall order minus 1. The overall order is just the sum of these exponents, 2 plus 3 is 5, minus 1 to address that molarity that was on top here. And so that's where we're ending up with to the negative fourth. By the way, again, either of these two formats are appropriate, so it's a kind of a take your pick. If I changed the temperature, that would end up changing this value. Keep in mind is that as temperature increases, my rate would increase, and so therefore I should see an increase of K if my temperature increases. All right, so the next thing they ask us to do is to write a temperature-dependent rate law expression, and that is with K plugged in. So I would write this as rate equals my K, which is 1491, and I'm going to go ahead and put the units of seconds to the negative first, molarity to the negative fourth, and then I'm going to have A raised to an order of 2, and B raised to the order of 3. And so now, as long as I ran my reaction at the same temperature, I could plug in whatever values of A and B I wanted to and figure out what my rate should be. So, for example, let's see one like that. It says here on this next part, hey, if the concentration of both reactants were increased to where now A is 6 molar and B is 8 molar, what is the new rate of their reaction? Well, first off, hopefully we notice those concentrations are way bigger than anything they ran this reaction at. And so therefore I should see a rate much bigger on producing C than anything that was in the table. So all I need to do now is plug in. Rate equals, and I'm going to do this without units. We'll talk about units at the end here. So I'm going to have 1491. We said that A is now going to be 6 molar. That's going to be raised to an order of 2. B is now 8 molar, raised to an order of 3. And when you plug this in your calculator, what it ends up getting is an answer of 2.7 times 10 to the 7th. You notice that is a way bigger value with that 10 to the 7th than anything that was in the table, but it should be because these concentrations are so much bigger. Now, as far as your unit for rate, it should match the unit for rate that you saw for all of those other trials. And so therefore, I should be in terms of molarity per second here. Last but not least, this is a throwback to something we talked about the other day. It says, hey, given the reaction in the previous examples, by what factor would the rate change if concentration of A is tripled and B is decreased by 1/2? So this is kind of doing what we did the other class where we say, hey, if A is tripled, tripling A would get raised to an exponent of 2, an order of 2. Doing that 1/2, that would get raised to an exponent of 3. And so the two effects are going to multiply by each other. Now, when we do that math, that gets a value of 1.125. So what that means is that I would go 1.125 times faster if I change those concentrations by those factors. This one is a little weird because we have the half. The other day we saw things like doubling or tripling and putting that value in there. And so I wanted you to see one where it actually is doing something where we're decreasing it versus increasing it. And so you can see what happens is 3 squared is normally 9 times faster, but because that change of decreasing the concentration would slow it down, it kind of ends up canceling out some of the effect of tripling A. All right, we're going to go ahead and pause there. I'm going to have a second video where we look at 2 more examples with these differential rate laws. If you have any questions or need any help, please feel free to email me. Bye, guys.